Okay, hello Precalc C. We've been learning about sequences for the past few weeks, past week and a half, and there was some homework over Halloween weekend when we had basically no school for a week. I had you watch a video on arithmetic sequences, and there were some homework problems, and I said, you know, we don't have time to go over them in class, so I would make a video. So here's that video. And there are some of these problems I definitely want to do, and others, you know, maybe they're so easy that we don't need to go over them. 9.1 was an introduction to sequences. 9.2 was specifically looking at arithmetic sequences, and 9.3 geometric sequences, which we did the previous class. So, okay, let's go. The first problem that was pretty interesting, I think, was this problem from section 9.1, and it was all about the Fibonacci sequence. So, okay, let's go over it right now. Here we go. The Fibonacci sequence. Okay, this came from this Italian mathematician, Fibonacci. His real name is something else. I can't remember. From the 12th century, and he was looking at rabbits. More on that kind of later. So here's the definition. It's just the definition you've seen before, maybe with some slightly different terminology. So they tell you that the first term and the second term are 1. That's pretty normal. And then here we say, well, the term n plus 2 is just term n plus 1 plus term n. Okay, so yeah. So of course this is just saying add the two previous terms. I guess the only thing nice about this formula is it sort of lets you start counting at n equals 1. So for n greater than or equal to 1, this is the correct formula because it tells you already what the third term is the first time that you can use that recursive formula. Okay, great. So just to make sure, just in case the textbook, in case you've never heard of the Fibonacci sequence before in your entire life, they say write out the first 12 terms of this sequence. Okay, let's do this right now. 1, 2, 3, 5. I'm just doing it now live on the spot. 8, 13, 21, 34, 55, 89. Not sure when I can stop, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So one more. So 144. Hopefully that's right. Yep. Okay, great. That was pretty easy. That was part A. Part B. Part B, they introduce an entire other sequence. So that's kind of interesting. So here we go. They say, all right, consider the following sequence, B sub n. And what is B sub n? Here they give an explicit formula for B sub n. It's the ratio between the next term in the Fibonacci sequence and the current term, something like that. Okay, I find this a little bit weird that they say for n greater than or equal, for n greater than 1. I'm just going to ignore that, and I'm just going to start counting at 1, because I think it makes it a lot more reasonable that way. So I don't see any reason why we should not be calculating B1. Because what is B1? Well, B1 is, if we're just following the formula, this is half of what this is just practice. B1 would be A2 over A1. In other words, the first term in this B sequence is the ratio between the second term and the first term of the Fibonacci sequence. Okay, so that's just 1. What's B2? B2 is the ratio between A3 and A2. In other words, 2 and 1, so that's 2. B3 would be the ratio between A4 and A3, so 3 and 2, so we get 3 halves. In general, what do they want us to do? Write out the first 10 terms? That seems a little bit excessive. But okay, here we go. 1, 2, 3 halves, 5 thirds, 8 fifths, 13 eighths, 21 over 13, 34 over 21, and this is just going to keep going, right? 55 over 34. I don't know when to stop. Maybe that should be good enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so far I'm maybe unimpressed or something like that. Okay, if we were doing this live in class, I would, turn on the Promethean board right now and or tell everyone to grab their calculator or something like that, because something quite amazing, if you've never seen this before, there's something quite amazing that happens which is that these numbers are getting really, really close to each other. And in fact, gosh, let's see. I don't feel like turning my whole camera on or off or doing something like that. So instead, I will just, you just can kind of trust me, or you can just, check this out or whatever, right? This is, of course, this is like 1.5. I can do some of these in my head. This is 5/3. That's just like 1.6 repeating. 8/5. What's that? That should be something that we know. That's just like 1.6. Man, am I doing something wrong here? I didn't expect them to go up and down like that. Make sure I don't embarrass myself. It is true that 5/3 is 1 2/3. It is true that 8/5 is 1 3/5. So yeah, I guess that's just true. And now we can do some more of these. 1 second. Boom, boom. Cha. Oh my god. Answer. Yeah. So then what's 13/8? I think I can even do this one in my head, right? Because that's just like 1 5/8, so that's 1.625. So now we're going back up. What's 21/13? Now I really need a calculator for the first time. So that's 1.615. So that's interesting. So we did go sort of up and then down and up and down. So that's kind of nice. But all right, maybe you're seeing where this is going. 34/21. 34 divided by 21. This is a riveting video here. This is 1.619. And all right, oh my god. It was 55 divided by 34. Okay, 1.617. And all right, pretty soon, it doesn't take very long actually for one to see that this sequence is going somewhere. Okay, and that's actually the study. That's actually the next subject that we're going to talk about. Today in class. So before even you watch this video, we will have discussed that this sequence has a kind of a destiny to it. And okay, it's hard to make that concept precise. The actual term we use for this is limit, so we say that this sequence has a limit. And informally, what that means is that this sequence, the sequence of ratios, is of the Fibonacci sequence, is going to some very particular number. Okay, what is that particular number? Well, I don't know. There's more to this problem. Let's do the other half of this problem. The other half of this problem says, quite interestingly, although they don't really have you follow up on it, they say, all right, let b sub n be 1 plus 1 over, no, sorry, not let, show that, so prove, so this is, now we have a little sort of math proof on our hands, prove that b sub n is 1 plus 1 over b sub n minus 1. In other words, just to kind of clarify here, we have defined the Fibonacci sequence. We've defined this B sequence as the ratio between terms of the Fibonacci sequence. And now we are going to prove that something which is I think not obvious at first at all, that the terms of the B sequence follow this pattern. In other words, this recursive rule can sort of tell us that we can kind of generate the next term of the Fibonacci sequence, the next term of the B sequence from the previous term. Okay, how should we go about this? So you're now being asked to do what in my opinion is like real mathematics, which is to prove, some theorem, or I don't know, close to real mathematics. How can we do this? I think the best way to do it is just do it. This is like some kind of identity, like a trig identity or something like that. So to establish that this is true, I need to kind of just show that I can derive one of the sides from the other. And so the thing to do, in my opinion, would be to start with 1 plus 1 over b sub n minus 1, and to verify that that is, in fact, the nth term of the B sequence. How? Well, by just doing some algebra and using the definition of B. Alright, so being kind of careful now, if this is what we're starting with the right-hand side, what does that give me? Well, I can get a common denominator, of course. If I get a common denominator, then that's b... Is this what I want to do? Sure. B sub n minus 1 plus 1 over b sub n minus 1. What do I have to say about that? No, I changed my mind. That's not a good idea at all. What I want to do is just reach immediately for the definition of this B sequence. What is the definition of this B sequence? Well, we defined it in terms of the Fibonacci sequence. So this is really like 1 over, what is B sub n minus 1? Well, B sub n is the ratio between the next term in the Fibonacci sequence and the current term. So B sub n minus 1 would be the ratio between A sub n and A sub n minus 1. Note my use of parentheses to clarify the sort of order of division there. But okay, this is just, dude, just stick in n minus 1 for n, basically, in the formula, which defines b. Okay, now I sort of got rid of b, so to speak, and now I have it, okay, let's keep going. So this becomes 1 plus 1 over that becomes a sub n minus 1 over a sub n. Now what? Now get a common denominator, and that's a sub n plus a sub n minus 1 over a sub n. But now, by the definition of the Fibonacci sequence, what is a sub n plus a sub n minus 1? Well, it's just a sub n plus 1, because that's how the Fibonacci sequence works, right? The recursive rule which characterizes the Fibonacci sequence is that when you add up a term and the previous term, then you get sort of the next term. Okay, and this is, by definition, b sub n. And so we sort of did it. It was a little bit mindless, although there was some sort of thinking, definition use involved or whatever. Okay, so I have this kind of a formula here. What should I make of this formula? What does it kind of tell me? It sort of tells me, hey, if you want to, you can, if you supposing you cared about this sequence b for some reason, if this b sequence was really important to you for some reason, then instead of computing it as the ratio of terms of the Fibonacci sequence, you could crank out these the terms of this b sequence by simply starting with the first term of the b sequence, which is just 1 after all, because b sub n is a2 over a1, which is just 1. So b1 is 1, and then to calculate subsequent terms of the b sequence, I just take the previous term, reciprocate, and add 1. So b sub 2 would be reciprocate, add 1. So it would be 1 over 1 plus 1, which is of course just 2. That's what we got. Okay, what's b sub 3? B sub 3 would be reciprocate, add 1. So take the reciprocal of 2 and add 1. And now we get 3 halves, of course, which is the next one. Now, how do we get b4? According to this rule that we proved, that you can get b4 by using the previous term of the b sequence. So reciprocate, add 1. So we take 1 over 3 halves plus 1. Okay, and what is that? Well, that's 1 plus 2/3. That's 5/3. Let's just do one more. b5, how do you get it? Reciprocate and add 1. So I take my number, which was 5/3, and I reciprocate it, add 1. And what is that? It's 1 plus 3/5 is 8/5, and that is b5. Okay, and so now that's providing sort of another kind of perspective on everything that's going on here. Okay, here's where the problem stops and doesn't ask you to do anything more. But I do want to do something more. Specifically, I want us to sort of think about where is this sequence going? And all right, if you get out your calculator right now, and or some other kind of technology, and you just perform this operation where you reciprocate, add 1, reciprocate, add 1, reciprocate, add 1, you can generate sort of arbitrary numbers of terms of this sequence, and you're going to get something that looks a lot like 1.618, you know, and okay, depending on what middle school you went to or how much math you know, that number might jump out at you, or you might be like, I have no idea what that number is, depending on also how much math Kirk taught you last year. So that's phi. All right. What's phi? Phi is the golden ratio. And there are a couple different ways of thinking about phi. The sort of traditional way of talking about it is you have some kind of segment, and the segment has some kind of length, say x. And to divide this segment up into the golden ratio is to divide it up into two pieces, call them 1 and x minus 1, such that the ratio of the whole to the large part is the same as the ratio of the large part to the small part. Okay, so this is then that x over 1 is 1 over x minus 1. I hope I did that right. I think I did. Okay, that's the kind of maybe traditional ancient Greek way of talking about the golden ratio. It's a ratio you divide a segment up into such that the larger part is to the whole as the smaller part is to the larger part. But for those of you who have learned your math from MCPS, I think that the exposure you had to the golden ratio, if you had any, was via the so-called golden rectangle. This now phrases as kind of an application of polygon similarity or something like that. So what is a golden rectangle? A golden rectangle is a rectangle in which, and it is alleged pretty unscientifically that the golden rectangle has all kinds of aesthetic properties. I think I had it better the first time actually. What makes a rectangle a golden rectangle? Well, if you, here's the defining property, if you cut a square out of it, oh man, let's try that again. If you cut a square out of it, so just let's humor me that looks a lot like a square, it's not terrible, then what remains is is also a golden rectangle. So it's kind of a geometrically recursive definition. A golden rectangle is a shape such that when you remove a square from it, it's similar to itself. Okay, and one way we can set this up is to let 1 be the side length of the square that we remove, and let x be, is this what I want to do? Maybe, well, it doesn't really matter. Maybe I want to make the whole thing x. Sure, no, I can make this x. So x, 1, x to 1, no, I do want it the other way. Let's make this x, and the whole thing becomes x plus 1. So let this be x, and this little bit 1 here. So, alright, this is sort of inconsistent with what I did above. Maybe I'll just make well, too bad. Okay, of course, what does it mean then? If this rectangle is a golden rectangle, then so what? Then what should be true is that the big rectangle is similar to the little rectangle, which is to say that the long side of the original rectangle, x plus 1, is to the short side, x, as the long side of the rectangle remaining when the square is removed is to the short side, which is 1. And we can now solve for x. And, well, let's just do it, right? This is now just an algebra 1 problem. So what we get is x plus 1 is x squared by cross multiplying. And so we get x squared minus x minus 1. This is also what we got over here, by the way, in a slightly different form, right? We also get x squared minus x equals 1. So it really is the same equation. And how do we solve this equation? Well, we just do it. It doesn't factor, so we can use the quadratic formula. So we get that x equals negative b, so 1 plus or minus the square root of b squared, so that's 1 minus 4ac all over 2. And so what we get is 1 plus or minus root 5 over 2. Now, root 5 is bigger than 1. Because this is ratio is defined as a sort of geometric object, we just ignore the one which is negative. And so to solve this particular geometry problem, we find that if you're going to cut a square out of some rectangle, leaving sort of 1 behind, then that x must be 1 plus root 5 over 2. Okay, but of course that is then just the ratio itself, because if what we're actually interested in is the ratio, then the ratio of x to 1, the so-called golden ratio, is the ratio that a rectangle must be in order for it to have this property. Well, it's just the ratio of the long to the short. And so the ratio of the long to the short here is x to 1. And so we hereby define this ratio phi, this number phi, this irrational number, 1 plus root 5 over 2. That's the definition. That's the sort of numerical definition of phi. But the algebraic definition of phi is it's this ratio. And of course you get the same thing over here, right? Because here if you solve for x, because it's the same equation, you're going to get the same answer. And once again, maybe it's easier to see in this case that that is the ratio, right? The ratio of the whole to the long is phi. Okay, and phi has these kind of amazing properties. What are those sort of properties? Actually, you can see it quite well here. Maybe is one way of seeing. So I'll put a little box around phi. I'm just going to kind of squeeze this into this little spot. Yeah, looking at this equation right here, which says that x plus 1 equals x squared. Well, if you want to think about phi geometrically, which is how I've presented it, then it's the golden ratio. It's the ratio that a rectangle has when it has this geometric property. But you could also think of phi as just the positive solution to this equation. In other words, what is phi? Well, it's the unique number which, when squared, is 1 more than itself. So phi, being a solution to this blue equation, certainly satisfies that phi squared equals phi plus 1. And that's kind of amazing, right? Phi is this number that, when you square it, what you get is something back which is 1 more than itself. And okay, this sounds kind of silly or something, but there's some sort of visceral impact that you get from maybe doing this on your calculator. Type in phi, hit the squared button, and what you get is this number which is 2.618, etc. It's exactly 1 more than itself. And then there's even another thing that one could do. So I'll put a little blue circle around this kind of math fact. And there's even another math fact, which comes from dividing both sides of this equation by x. If you do that, then you get that x is 1 plus 1 over x. In other words, and I'll put a purple box around this equation, which is just a minor manipulation of this equation over here in blue. Well, the solution to this equation is also phi. And so there's this sort of other amazing property, not unrelated but still worth mentioning. You can think of phi as the positive number which is 1 more than its own reciprocal. And I'll put a purple circle around this. I might be in the way of the camera right now. In other words, if you phi is this, that should say phi. Phi is this number which, if you reciprocate it, then what you get is a number which is 1 less than itself. Perhaps it's maybe even better to, well, I just leave it like that maybe. Okay, now are you starting to see the connection? I am. The connection is here. What is phi? Phi is the unique number, the unique positive real number, which is 1 more than its own reciprocal. Where have you seen this 1 plus 1 over phi? Well, 5 minutes ago, right? Here is the characteristic property of this B sequence. The property of this B sequence is that we proved in part C of this homework problem that each term of the B sequences can be generated by reciprocating the previous term and adding 1. Okay, and so let's now just clear a little space and kind of just wrap up this discussion, I think that's fine. What one may sort of do now is sort of think of this sequence as being kind of generated in a kind of a way where you reciprocate and add 1. So take sort of like 1, the number 1, and then as we did over here, sort of reciprocate and add 1. Okay. Now reciprocate, add 1. Reciprocate, add 1. This is sort of this very, very complicated fraction. This has a name. This is called a continued fraction. And if you do this literally forever, and so what it's easier because my board is getting bigger and bigger. So instead, maybe I'll put some dots down here to suggest that what I'm really going to do is sort of go forever on the inside, but it doesn't really matter which way you do it. Then this number, this is in fact phi. So phi is, we already agreed kind of by investigation or something like that. By investigation, we suspected that this sequence had a limit, and that limit was phi. We proved this defining property of this B sequence, that you can get the next one by reciprocating and adding 1. And then we sort of independently reminded ourselves about this phi number. And so what's sort of really kind of going on here is that what we sort of want when we see that this sequence doesn't change, then what are we looking for? We're looking for, okay, one more time. We have this number 1. Then what do? We reciprocate and we add 1. That gives us 2. We reciprocate, add 1. We get 3 halves. We reciprocate, add 1. We get 5/3. We reciprocate, add 1. That gives us, 8/5, etc. But far on down the sequence, say when we get to the 1,000,000th term, for example, right? The 1,000,000th term of the B sequence. B sub 1,000,000 or something like that. If I reciprocate and add 1, well, I'm going to get the next term, which is going to be the 1,000,000th and first term. But what I really mean when I say that this sequence has a limit, this is the best explanation, I think. What I really mean when I say that the sequence has a limit is that the numbers of the sequence are getting really, really, really close to each other. In other words, they're barely changing. In other words, once I go out to the 1,000,000th term, these two are pretty much the same thing. They differ by, by almost, 1/1,000,000th or something like that. In other words, if I wanted to know, going kind of about this in a roundabout way, if I wanted to know what is the number that this sequence is getting closer and closer to, what I need is a number which, when I perform the operation of reciprocating and adding 1, gives me back basically the same number. I'll say that one more time. I proved that this sequence has the property that if I take a term of this sequence, say the 1,000,000th term, reciprocate and add 1, I get back the next term of the sequence. But if this sequence has a limit, and informally we've determined that it does, then what is that limit? Answer, the limit of this sequence, the number that the sequence is getting closer and closer to, must be a number that has the property that when you reciprocate and add 1, what you get back is basically the same thing. Okay, so what is a number which when I reciprocate and add 1 barely changes that number? Well, the answer is phi, right? Because now if you want to, you can multiply through by x, and you get, x plus 1 is approximately x squared, and so now we're solving this equation, and the answer to this is phi. In other words, phi is the limit of this sequence because phi is the unique number which is equal to its own reciprocate add 1 operation. Okay, and having sort of proven all that to you, then the last thing to sort of say is that this is a sort of, this is called an infinite fraction. Well, it's not called, it is a kind of infinite fraction. It is called a continued fraction. And this thing that we see here is the continued fraction expansion for phi. So one can represent this irrational number phi as this sort of 1 plus 1 over, 1 plus 1 over, 1 plus 1 over, and if you do that sort of forever, then you get the number phi. And if you truncate this continued fraction at any point, say here, well then that gives you the, whatever it is, 5th term or something, 4th term of the B sequence. And the more out you go in the continued fraction expansion, you're actually just generating the terms of the B sequence, and the limit of that B sequence is phi. Okay, goodbye for now. Okay, hello everyone, we are back. We are going to go over the problems from section 9.2 on arithmetic sequences. I think we can do this in about 15 minutes. They're all pretty easy. These are problems I never usually go over in class. Another thing that's happening is there are 2 small children in the room who want to be involved. Do you want to say hi to the camera? Ada, say hi.
Hi.
Okay, and then there's another little one here who doesn't talk yet, but he's going to make some noise. Okay, so we're just going to, this is not a very important video, so we're just going to kind of push on and do, oh, we have some animals too. Woo. Okay, let's go. Section 9.2 was all about arithmetic sequences. And so, okay, what were these problems? They started off pretty easy. They were just like, yo, is this even an arithmetic sequence? So we have 1/3, 2/3, 4/3, 8/3, 16/3, and then there's this kind of dot 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 situation. Alright, well, is this an arithmetic sequence? Well, the answer is just no, right? Because what's an arithmetic sequence? It's a sequence which is increasing by a constant from term to term, and this just isn't. Right here we are going up by 1/3, but here we're going up by 2/3, here we're going up by 4/3, here we're going up by 8/3, etc. So the answer is sort of no. Okay, that was fun or something like that. How about number 8? Number 8 says, oh, here we go. This sort of the sequence of natural logs of the positive integers. So ln4, ln5. All right, this might initially befuddle you for a minute. This is kind of an opportunity now for us to look at some properties of logarithms. Okay, well, first of all, ln1 is just 0. So if we're charting the gaps, how much do we go up by? ln1 is 0. So here we went up by, so I'll just write, plus ln2. Here, I guess I should put pluses here to indicate that we did sort of go up by that amount. So this is now, I'm looking at the sequence of gaps. Okay, what's the gap between ln2 and ln3? Well, what is ln3 minus ln2? This is...
I don't know.
You don't know what it is? I'm talking to the camera, Ada, but if... Okay, ln3 minus ln2. Well, there's a log property which says that ln a over b is ln a minus ln b, so this problem is just slightly reinforcing that. What is ln3 minus ln2? Well, it's just ln3 halves. So whatever that is. So here, I have gone up by ln3 halves, and I sort of already can now tell you that this is not arithmetic because ln3 halves is not equal to ln2. And okay, but just to do kind of one more of these, what's the gap between ln3 and ln4? Well, ln4, I'll squeeze it in right here, ln4 minus ln3 is just ln 4/3. And okay, so here we're going up by ln 4/3, and here we're going up by ln 5/4. And as those numbers are all different, then this is, once again, this is not an arithmetic sequence. Okay, good. That's just kind of over to the sort of definition of what an arithmetic sequence is. Now there are these like little problems. They're basically like almost like SAT problems or something. They're so sort of just simple, but I don't know. Maybe we should go over them. 25 just gives you an arithmetic sequence. It tells you that it's arithmetic. So there's no guessing. So it's 4 3 halves, -1, -7 halves, etc. And the question is. What is the question? Find a formula for the given arithmetic sequence. Okay, so just give me... Oh boy. Off camera you can't see because they're too short. Just two little kids just walking all around checking things out. Okay, though I want an explicit formula for the nth term of this arithmetic sequence. Well, I think I can do that because what's happening here is I am going down by 5 halves, right? And here I am going down by 5 halves, and here I'm going down by 5 halves. So D is negative.
Izzy wants to help you.
Izzy wants to help me?
Yeah.
Okay, I'm getting help from a stuffed bear. So Izzy's gonna help me now. Thanks, Ada. I did need some help. Okay, so Izzy is gonna help me teach math. So D is negative 5 halves, and of course the first term is 4. So what's the generic nth term then of this sequence? Well, it's going to be every term of this sequence is going to look like 4 plus a bunch of negative 5 halves. How many of these negative 5 halves do I have? Well, it depends on what term I'm on. When I'm on the second term, I've added negative 5 halves once. When I'm on the third term, I've added negative 5 halves twice. When I'm on the nth term, I've added negative 5 halves n minus 1 times. And so that's why that is the formula for the nth term. Okay, Izzy and I are going to do another problem now. Okay, good.
I can look up there. It's too high.
You can't look up there because it's too high? I think your head is on the camera now, though, Ada. Okay, so now, number 29 just makes you jump through some tiny hoops. They tell you that the third term is 94, and the sixth term is 85. Okay, so how should we do this? I mean, I think the best way to do this is just kind of do it, right? So you just... Oh, I'm sorry. Izzy's supposed to help me. Izzy, what should I do next? Well, I don't know what the first term is, I don't know what the second term is, but I do know that the third term is 94, and the fourth term I don't know, the fifth term I don't know, and the sixth term is 85. So I don't know, this kind of thing is, I think it's common sense, but it might help you a little bit. So what can I do for making this little picture? What do I see? Well, I see that, of course, to get from the third term to the sixth term, I must add 3 times whatever the common difference is, which I don't know. So the sort of systematic way of doing this is to say that 94 plus 3 of these common differences should give me 85, and this sort of shows that that D must be negative. Well, what is that? Then I just subtract again negative 9. So 3D is negative 9, so D is negative 3. Does that check out? It just does. If D is negative 3, if I'm going down by 3 every time, well then what can I say? Then this must be like 97, and this must be 100. So that's pretty much it. And therefore, what does the generic term look like? It looks like the nth term must be 100 minus 3 n minus 1.
Why is he not doing any coloring?
Oh, Izzy should be doing the drawing also?
Yeah.
Okay, the bear is going to do some drawing also. Okay, let's go to 31. No, I know. Izzy's going to do it. Hold on. Izzy's going to do this next one. Write the first 5 terms of the arithmetic sequence. The first term is 5 and D is 6. Okay, so the first term is 5. Ada, are you watching? And D is 6. Good job, Izzy. And we're supposed to write the first 5 terms. Okay, this is kind of a silly problem. Even a stuffed bear can do this one. Because the first 5 terms are 5, 11, 17, 23, 29, and 35. Hopefully I did that right. Good. 35. Good job, Izzy. I didn't know you were so good at math. 35 says the first term is 3 halves. The first term is 3 halves, says this problem. And subsequent terms, they use k. No, don't turn the page. The subsequent a sub k plus 1 is a sub k minus a fourth. A sub k plus 1 is a sub k minus a fourth. Okay, how are we going to do this? We just do it. This is also kind of like very easy. Even a bear could do it. Okay, Izzy, what should we do next? Well, the first term is 3/2, and then to get each term, you just keep subtracting by fourths. So that's like 6/4. So that's 5/4, 4/4, 3/4, and 2/4. First 5 terms. Okay, good. 39. You might think that these are almost not worth doing, but all right. 39. The 8th term is 26. 39. The 8th term is 26, and the 12th term is 42.
No, I Izzy to do it.
Okay.
Izzy.
Izzy, what should we do next? I think we should make a picture. Okay. So once again, maybe now I'll just not draw all of them out. But this is the 8th term, which is 26. I don't know the 9th term, 10th term, 11th term, and now the 12th term is 42.
Izzy should be doing it.
Izzy should be doing it? Yeah, that's good. Yeah, don't just watch your teacher do the math. You have to do it yourself if you want to learn. That goes for students and also bears, right?
Yeah.
Yeah, okay. So, anyway, 8, 9, 10, 11, 12.
No, Izzy
Izzy has
has to be doing it.
to be doing it. Okay, so how many times? How many times do I add D? Of course, it's 1, 2, 3, 4. So if the 8th term is 26, then whatever D is, I don't know. But I have to add D 4 times to get 42.
I don't know what you're talking about.
I don't know what you're talking about. So if I subtract 26 from here, I get 16.
I don't know it.
So D is 4. And if you have a lot of time, you can always check this.
This is what I know.
I'm going to do this one, Izzy. So that's 30, 34, 38, 42, so it all checks out. Okay, wait, we have to do some more things. So we have to now go back, and we have to figure out what the first term is. What is the first term? Well,
Can I just make a picture?
you can't make a picture yet, soon. But I know that to get to the 8th term, I would have to add D 7 times. So the first term plus 7 times 4 would give me 26. And so that tells me that the first term has to be -2. Once I know that the first term is -2, then one simple way of writing out the general nth term is it's going to be -2 plus 4, D is 4, so 4 times n minus 1. So I add 4 n minus 1 times to the first term, which I determined was -2. Okay, let's do 3 more before we stop this video. We just did all of these, all of which I would categorize as common sense, but maybe it's good to have some direct instruction on how to set this up.
See up there.
You can't see up there? Yeah, you're not really tall enough.
Yeah.
Okay.
I can't even see up there.
You can't even see up there? Maybe you should take a couple steps back from the board.
Okay.
Oh, now can you see everything?
Yeah.
Whoa, what a great idea. Okay, so now we do number 45. Finally, we get to the sort of big subject of this whole thing, which is finding the sum of the first n terms. So what's 45? You take Izzy for a minute. In 45, they give you the following sequence: 40, 37, 34, 31, etc. They tell you it's arithmetic, and they want the sum of the first n terms. Okay, so as I said in the video, there are basically 3 different ways to do this. The maybe best way is just to learn. The best way is just to learn the formula. And we derived the formula on that video from a week and a half ago. Please don't open that. Please don't open that. The sum of the first n terms of an arithmetic sequence is n over 2 times 2a plus n minus 1d. Okay, notice I hesitated for a second, even though I'm a math teacher and I've been doing this for 15 years. You know, the weak link of any formula is forgetting it or forgetting even what the whole point of everything is. And here, okay, a is the first term, n is the number of terms, d is the common difference, and that is the right formula. if that's what you got, then this whole thing is just kind of becomes just a simple plug it in kind of situation. If I want the sum of the first 10 terms, I just plug in 10 for n. I get to 10 over 2 twice a, which is 40, plus n minus 1, which is 9, times d, which is clearly just negative 3. And whatever that turns out to be is just going to be the answer. 80 minus 27. Ada, what's 80 minus 27? 53, I guess? Yeah?
54, I guess.
50. 80 minus 27 is 53, so it's just 5 times 53, so it's 250 and 15, so it's just 265. Okay, so that's one way of doing it, this problem. Another way of doing this problem is to sort of remember a different formula, which is arguably more intuitive, which is that the sum of the first n terms is just the average of the first term and the nth term. So that's the average of the first term and the nth term. That kind of tells you what the average term of this arithmetic sequence is. After all, because it's arithmetic, the first term and the nth term are sort of symmetric about the center, but so are like the second term and the second to last term, etc., etc. So if you just take all those terms and you multiply by n, that should give you the sum of the first n terms. Let me say that again. If I want the sum of the first n terms, what I could just do is multiply the number of terms by the average term. And the average term is going to be just the average of the first and last term. Okay, and the only drawback of this is that I first have to calculate what the nth term is. So what is the well? Okay, so I think you can see that this is really just the same formula, of course, because what's the first term? The first term is 40, and what's the nth term look like? Well, to get to the nth term, I have to take 40 plus 9 of these negative 3's. So of course I'm just doing the exact same thing, and the answer is 265. Okay, then the other way, the sort of third way to do this problem, is to kind of redo the logic of the entire proof. What do you want? Okay, so what am I really trying to do? I'm really trying to add, so I'll call it S sub 10. I'm trying to add 40 and 37 and all the way up to the nth term would be, what is that, 13, I guess. 40 minus 27. Okay, how can I add up all these numbers which go down by 3 every time and terminate with 13? Well, I can sort of think of that same sum a different way by flipping the order. So now this is 13, 16, 40, and then adding them up. And if I add up these two equations, I get twice the thing I'm looking for is, well, that's 53, but that's also 53. And of course, these are going to be all 53 because I'm going up, but I'm going down by 3 along the first equation term by term, and I'm going up by 3 along the second equation term by term. So this is also going to be 53. How many of these 53s do I have? 10 of them. And that's where we get to 2 times S sub 10 is 53 times 10. And when I divide, I get that S sub 10 is 53 times 5. So I get 265. This to me is in some ways the most honest. No, don't draw on the wall. You did draw on the wall. This is the most honest way of doing this calculation because you're actually sort of doing mathematics as opposed to just chugging through the formula. But it's not, it's not the most efficient way. Okay, 2 more problems, which are just, I think, just 2 more opportunities to use this same formula again, and then we're gonna go do some parenting. Although this is kind of parenting. Ada, are you enjoying this?
No, I just want to make pictures.
You just want to draw pictures?
Yeah.
Okay. So here we go. This is 57.
No,
Do you want to draw some pictures right now?
not my pictures.
You just want to draw regular pictures?
Yeah.
Okay, can you reach to draw it on this board? Okay, here, take the blue. You can draw some pictures right here. Okay, but make sure to not draw on the wall. Okay, good. So, what's...
But you use all, some of the board is kind of gone.
Some of the board is kind of gone?
No, the blue.
Oh, the blue is, some of the blue is kind of gone?
Yeah.
Okay. Okay, 57 says, take the sum from n equals 1 to 20 of 2n plus 5. Okay, how can we do this problem? In my opinion, for students who are just learning this stuff for the first time, don't try to be cool and fancy. The best thing to do with the sigma notation probably is to kind of get rid of it. Actually, I guess I'm going to do this problem in two different ways. One way, the very casual way to do this, is to just recognize that the sigma notation is a very efficient way of writing summations, and yet to also recognize that it's not a very sort of human, helpful way to write these. And so let's just kind of undo the sigma notation. This is what I think what I would recommend for most of you. What am I saying? What I'm saying is just plug in n equals 1. So interpret this symbol as meaning the sum from n equals 1 to 20 of expressions of the form 2n plus 1. Theo, no. What about when you plug in 1? What do you get? You get 7. When you plug in n equals 2, what do you get? You get 9. When you plug in n equals 3, what do you get? You get 11. And then just keep going out until n equals 20, in which case this is 45. In other words, I have just translated this problem in sigma notation to a problem in casual, informal, dot notation, which is less efficient and maybe less precise. Yeah, you messed up there. Don't worry about it. But now easier to work with in some sense. So, okay, now this just becomes another problem like the one we already did. I have sort of 20 terms. They all look like this. D is 2. So if D is 2 and A sub 1 is 7,
Papa, look at
then
this.
I want the sum. That's a very nice picture. I want the sum of the first 20 terms. What is that going to be? It's going to be 20 over 2. I'm using this formula right here. Times twice the first term, so 2 times 7, plus n minus 1, so 19 d's. And d we said was 2, so that's 38 and 14. What's 38 and 14? 52. So that's 10 times 52. So hopefully that's 520 if I did that. If I did that right.
I didn't really want to
14 and 38. You didn't really want to come up here?
I was just joking.
You were just joking when you said you wanted to come up here?
Yeah.
Okay, so wait, here is the other way to do this problem, which I think is kind of interesting, is to use properties of sigmas. Okay, so this is something I've meant to do for years. I just never did it. Please keep your drawing over on this side. Okay, what do I mean by that? Well, what's happening here? We're adding up 20 things. Those 20 things are all of the form 2n plus 5. So instead, I'm really adding sort of 2 things 20 times. Well, because addition is commutative and associative, and therefore it doesn't matter in what order you do things, instead of adding 2 things 20 times, let me add 20 things twice. By that I mean, I shall break this up into the sum from n equals 1 to 20 of 2n plus the sum from n equals 1 to 20 of 5. In other words, I think this is clear, right? Instead of adding 2n plus 5 for n from 1 to 20, let me add 2n from n to 1 to 20, and let me add 5 from 1 to 20. And I'll do one more thing, which is here, instead of adding 2n 20 times, 2 times n, let me instead add n 20 times and multiply that by 2. So what we are sort of discovering here are various properties of sigma notation, or properties of summations, would be a better way to put it. It's not a property of the notation, it's a property of the actual math that's going on. I hope you will agree, what I've just done here is to say that it's legitimate to just factor a 2 out of this summation. Why? Because whether you first multiply each of your n's by 2 and then add them all up is irrelevant. I could first add them all up and then multiply by 2. This is just the distributive property. The justification for this step is just the distributive property. Okay, what is the advantage of doing all this kind of theoretical work? Well, now, instead of using any sort of properties of summations, I can just say, what are the sum of the numbers from 1 to 20? Oh, that's just the basic formula that we did on the first day of this unit. That if you take the sum from I equals 1 to n of I, which is just another way of saying 1 plus 2 plus 3 plus all the way up to n, then that is just n plus 1 over 2. That's the thing that we proved / discovered on the first day of this unit. That's the sort of original Gauss story. So, what are the sum of the numbers from 1 to 20? Careful, Ada. It's going to be 20 times 21 over 2. And what are the sum, what happens when you add 5 20 times? Well, you just get 100. Therefore, every single one of these sum of an arithmetic sequence problems can be reduced to a sort of summation over like a polynomial or something like that. And now, what do we get here? Hold on, Anna. 20 times 21 is 420.
Tell Izzy what this is all about.
And the answer is 520. I'm going to tell Izzy what this is all about. First, we need to do one more problem, and then we're going to stop this video and go downstairs, okay?
But I want to make some more pictures.
You want to make some more pictures? Okay. So, last problem, 64. Not something that's particularly important, maybe. But what does it say? It says, this is not something we talked about in class. The problem says, insert k arithmetic means. But in this case, k was 4. So insert 4 arithmetic means between 2 and 5. Okay, so doing this problem is not hard, but probably understanding what they're even talking about and why I should care maybe is the hard part. The idea is that here's 2, and I just want 4 numbers in between 2 and 5. Ooh. So insert 4 arithmetic means between 2 and 5 says that I basically want to insert 4 numbers in between 2 and 5 such that they form an arithmetic sequence. And, okay, why should I sort of care about this? I don't know, maybe you have 2 of something and in 5 days' time you want there to be 5 of something, and so you're sort of asking the question, hey, how do I sort of spread things out, or something like that. Okay, anyway, let's just do the problem. What should we do? Well, we have to add 1, then we have to add, or we have to add something, we have to add it again, then again, then again, and then again. In other words, I have to add 5 times. If I want to insert 4 arithmetic means, then there are 5 gaps. So this whole problem reduces down to 2 plus 5d is 5. And, okay, so 5d is 3, and d is 3/5. And so, that's it. Oh, so no, I guess I have to still do it. So what are so that's 2 and 3/5, so that's 13/5, if I did that right. Yeah, and now add 3/5, so that's 16/5, and 19/5, and 22/5, and then 25/5 is 5. So, there we go. Okay, that concludes, thank you, arithmetic sequences. What did I say, 10 minutes? I'm sure that was a lie. 28 minutes. Goodbye. Kids, say goodbye.
Bye.
Okay, back for part 3. This is section 9.3 on geometric sequences. I think we should be able to do this really fast. Let's go. The first couple of these are just simple questions. Yo, is this a geometric sequence or not? So here we have 3, 12, 21, 30, etc. Question, is this a geometric sequence? 3, 12, 20, 30, yeah. Dude, no, of course not. It is in fact arithmetic. We go up by 9 every single time. Is it geometric? It just isn't. What does it mean to be a geometric sequence? Well, the ratio between a term and the previous term has to be the same. But the ratio between 12 and 3, also known as 4, is definitely not equal to this ratio, which is 7/4. Okay, and this 30/21, that's just the ratio of 10/7. So these numbers are all just sort of not equal to each other, and so this is no. Okay, good. Number 5. They give you another sequence and ask you if it is geometric. 1 1/2, 1/4, -1/8. Is this a geometric sequence? Well, I don't know. Let's check it out. I guess the answer is just yes, right? Here, the common ratio is -1/2. This can be seen by just doing it, right? What is -1/2 over 1? Well, it's -1/2. What is 1/4 over -1/2? That is also -1/2. And what is -1/8 over 1/4? Well, that's also -1/2. This is probably not the sort of simplest way to do this, but there it is. Okay, great. So that's 3, 5, so 6 now. What's up with that? 6 is 5, 1, 0.2, 0.04. Okay, well, I find these decimals to be kind of just a distraction, so perhaps we can just convert these back into rational numbers. So what do we have here? We have 5, 1, that's a fifth. 4 over 100 is actually just 1 over 25, and now we see, okay, so the answer here is yes, and the answer here is also yes, because in this case r is just 1/5, so we just multiply by 1/5 each time. Okay, I think that was pretty straightforward, so good, sort of three down, or whatever, boom, 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 boom. Let's do some more. Let's skip 8. It's not that exciting. Let's go straight to 15. What is 15? Here we are given a geometric sequence. Well, specifically, we are given that the first term is 5, and the r is -1/10, and we're just asked to write the first 5 terms. Okay, so this is just, dude, you just do it, right? The first term is 5. How do you get the next term? You divide by 1/10. So that would be, maybe I now do want to use decimals or something. No, I guess not. So that's going to be -1/2, right? 5 times -1/10 is -1/2, and I just multiply by -1/10 again. So that's 1/20th, and again, so -1 over 200, and again 1 over 2,000. So the size of this number is going down by a factor of 10 every time. And also notice, this is kind of obvious, but maybe worth mentioning, that when your common ratio is negative, then sort of every other term is positive and negative. Okay, good. 23 is one of these formulas where they make you kind of figure out some stuff, not even really. So a sub 1 is 6, and r is, oh, okay, and r is -1/3, and the question is, what is a sub 12? This is the question. Okay, a sub 1 6, r -1/3. What's a sub 12? All right, well, dude, if the first term is 6 and we increase by -1/3 each time, then by the time I get to the 12th term, well, what does the 12th term look like? It looks like 6 times 11 of these r's. I've multiplied by r 11 times, and so I don't think I really want to do this. So I might just leave it like that or something. I don't know what they really expect you to do here. But what are we going to get? It's going to be, this answer is going to be negative, and it's going to be basically -2 over 3 to the 10th, which is some giant number. So I think I stop there. Okay, 24, I think is kind of the same sort of thing, but maybe with one extra hoop to jump through. Nope, not at all, not even. Is it really so silly? I should have given you more kind of exciting ones. Too late. 24 says the first term is 8, and r is root 5. R is root 5. What is a sub 9? Okay, well, what is a sub 9? It's going to be the first term, 8, and then I've multiplied by root 5 8 times to get, by the time I'm on the 9th term. So what is that? That's 5 to the 1/2 to the 8th, so it's 5 to the 4th. So that's 8 times 5 to the 4th. I probably still don't want to really do that. Well, okay, if I'm being really show-offy now, 8 times 125 is 1,000. Yeah, so that's just 5,000. Hopefully I did that right. 625 times 8 is, yeah, that's probably true. Okay, now 2 more, and then we'll be done. I think with I should have done more. Should have done some more interesting problems. I realize now, but it's too late. Okay, so what have I just done? Boom, 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 boom. So 37 and 41. Let's go. 37 says, find the indicated sum. Okay, so this is similar to what I was saying in the previous video. I want the sum from n equals 1 to 9 of 2 to the n minus 1. Here I feel even more strongly that, beginning students who are in pre-calculus, who are learning things for the first time, should probably, no matter how smart you think you are, it's probably better to just get rid of the sigma notation. Just basically, in other words, accept the sigma notation as a very efficient way of writing what needs to be written, but when it comes time to doing the summations, just kind of get rid of it and replace it with dot dot dots. So when n equals 1, what is that? Well, that's 2 to the 0, so that's just 1. And then when n is 2, then that's just 2. And when n is 3, well, that's just 2 squared, that's 4. And I keep on going until I get to when n is 9, then that's just 2 to the 8th. In other words, just rewrite it like this, and this is now already a hard enough problem if you're just learning sums of geometric sequences. How do you do this? So there are a couple of ways to do this. This is the sum of the first 9 terms. Okay, the simplest thing to do is to just know the formula. What is the formula? I'll do it down here, I guess. What is the formula for the first n terms of a geometric sequence? Answer, it's A times 1 minus r to the n over 1 minus r. This is what we did in the video with the identical twin, magical cows, and everything. So here I want the sum of the first 9 terms. Here A is 1. Here r is just 2. So this is going to be 1 minus 2 to the 9th over 1 minus 2. Therefore, this is just negative 1 down here. That flips the sign, so this is just 2 to the 9th minus 1. And 2 to the 9th is 512. So this whole problem just becomes 511. Okay, the more sort of bold thing to do right now is to, maybe I'll put this over here. So this was S sub 9, right? If I wanted to kind of go through the logic all over again, what I could do is I could multiply this equation by the common ratio, which in this case is 2. So if I multiply this entire equation by 2, what do I get? Well, I get twice the sum of the first 9 terms. Should be, when I multiply 1 by 2, I get 2. When I multiply 2 by 2, I get 4, and etc. all the way out, till finally when I multiply 2 to the 8th by 2, I get 2 to the 9th. And then subtract these two equations. If you upside down subtract, then you get on the right-hand side, 2 to the 9th minus 1, and on the left-hand side, you just get s of 9. So this is just another way if you don't like formulas, or if you can't be bothered to remember them, or you feel it's sort of anti-intellectual or something to prove a formula and then just use it mindlessly, then you can sort of redo the logic every time, as I've just done here. Okay, let's do one more problem, and then we'll be done. Ooh, this is a wet sponge. Okay, so let's go. Okay, 41. What is 41? It's just another one of these same problems, but with maybe some just like more confusing and annoying stuff. Is it really just like the exact same thing? It's really just kind of the exact same thing. Perhaps we should do 44 instead, just for its... Let's do 44, because it's maybe a little bit more tricky. It's also even, so the answer's not in the back of the book. Okay, what's 44? It's the sum from n equals 0 to 15 of 2 4/3 to the n. Okay, this is a good example of, if you're very sophisticated, there are certain things you could sort of do here, but if you're not so sophisticated, this is kind of a drag, because this problem also sucks for different reasons, which is that these numbers are so big. Well, I guess the big problem is that here, because we're starting counting with 0, that means there's sort of we have to be a little bit more careful, like with our indices, and we don't want to get into any kind of off by 1 errors or whatever. So, yeah. So one approach to doing this problem, the one I probably recommend, is just to do kind of what I was saying already, right? Plug in 0 for n, 4/3 to 0 is 1, so therefore the first term of this sequence is just 2. And then when n is 1, I get 2 times 4/3, so that's 8/3. And when n is 2, notice I'm actually on the third term here, I get 2 times 4/3 squared. Maybe it's actually better to even just keep writing it as 2 times 4/3, etc. And now, being sort of careful, when do I stop? I stop at n equals 15, which is going to look like 2 times 4/3 to the 15th. But that's not the 15th term. This is in fact the 16th term. So all of our formulas assume that we are counting starting from 1. And okay, it's just true that if you're adding up this summation from n equals 0 to 15, 0 to 15 inclusive, that's actually 16 numbers. So it is important to realize that this sequence, that this sum has 16 terms in it. Okay, and since it has 16 terms, when I go to apply the formula, it's kind of annoying because the formula says that the sum of the first n terms is a times 1 minus r to the n over 1 minus r. But we are actually summing the first 16 terms because that last number we're adding is in fact the 16th term. So okay, so then what's a is 2, and what we actually get is 1 minus 4/3 to the 16th over 1 minus 4/3. And okay, 1 minus 4/3 is negative 1/3, so dividing by 1/3 is like multiplying by 3. So the answer we get here is 6 times 4/3 to the 16th minus 1. And I don't think it's any benefit to do anything more with this, so I'm just going to leave it like that, because those are sort of monstrously huge numbers. Was there kind of an alternative to this? Maybe just not. Maybe we just stop there. Okay, good. So we didn't do 41, maybe because it was kind of boring, but we did do 44. I think this is a good review of arithmetic sequences, geometric sequences, and everything like that. Goodbye, class.